Hello, my name is James Brenner, and this is my research in the inflow analysis for multi-rotor systems. I'm from Oklahoma State University in the School of Mechanical and Aerospace Engineering, and this research is sponsored by USRI Unmanned Systems Research Institution. The motivation behind this research is to be able to better map the atmospheric boundary layer, or the ABL. The ABL is important because this is where most of the weather activity starts. Currently, we have two main methods of measuring the ABL. The first one is weather balloons, which are only launched 2 times per day, and they travel upwards through the atmosphere in a vertical profile. These are great, but the downside is they only gather the data where they go. We can't control them, and they spend actual very little time in the lower atmospheric boundary layer gathering data. The second method that we have is mesonet towers. These are on the surface of the Earth, and they can gather data constantly throughout the day. The main downside of this is they only go up to 33 feet. So with these two methods, there's a pretty significant portion of atmospheric data that we're missing, and this is where unmanned aircraft come in. With UAVs, we can send them exactly where we want and take the data when we want and where we want it. And currently there are two main types of UAVs, fixed wing and multi-rotor UAVs. This is a OSU multi-rotor UAV system that we currently have. This exact system is fitted with a ultrasonic anemometer, pressure, temperature, and humidity sensor, as well as a CO2 sensor underneath. The benefit of a multi-rotor system like that is it has the capability of vertical takeoff and landing, and it can also hover in place, so we can hover, move it exactly where we want and take data for as long as we want. The downside that we have to this system is the inflow and downwash of the rotors can affect the sensors on board. This is where the motivation for this research comes in, is to be able to better understand the flow field around these small UAVs, so we can determine the optimal placement for our weather sensors. This research specifically is going to be looking at the inflow, which is above, directly above the rotors, and this is because this is where we are placing our sensitive wind, speed, and temperature sensors. So the idea was to use PIV, or particle image velocimetry, to determine the average velocity of the inflow of the rotor system. So here is the experimental setup and equipment. Down on the right is the water tunnel, Oklahoma State University, which was used for the PIV experiment. On the left is the diagram. You can see the camera on the outside, and then this is the test section, and then the rotor and laser plane, and then which is mounted to upside down to the lid of the test section. So this is so I could wire all the speed controller wires up through the lid of the tunnel, and that connects to the speed controllers powered by LiPo batteries, and then this is all controlled by a laptop. And then over here is a quick equipment list. I used 3-inch diameter propellers and a high-speed camera, and then the motors were Emax 930 kV brushless motors. For the rotor test configuration in laser plane, I wanted to test two multi-rotor systems, a dual and quad rotor system, to compare the difference between the number of rotors. So I started out with a DJI Phantom 4 and scaled that down to a small enough to it could fit in the water tunnel. So I have a diameter, the system had a diameter 4 inches with the 3-inch blades added on that has a total circumference of 7 inches. For the laser plane positions, I tested 3 positions rotor configuration. So for the first one is the dual rotor with the rotors parallel to the incoming crossflow, and with the laser plane positioned at the tip, mid blade, and hub. And then I only tested one side, as this is a symmetrical system. The top side should mirror the bottom side. And then for the second one, I tested dual rotors with the rotors perpendicular to the incoming crossflow, and I tested with the laser plane positioned at the tip, hub, and center in between the two rotors. And then the last configuration is the quad rotor, with the laser plane positioned on the far tip, the far hub, and then the center, capturing the leading hub and trailing hub, and then the exact center of the quad rotor system. For the testing matrix and Reynolds number, I wanted to vary two main parameters, the rotor angle and the free stream. For the rotor angle, I wanted to simulate the quadcopter in hover, which is 0 degree rotor angle, and then simulate it moving forward through a crossflow. So I increased the rotor angle to 15 and 30. And then for the free stream, I tested ambient conditions and then a half a meter a second. This half a meter a second in water is roughly equal to 10 meters a second in air, which is the average speed for most quadcopters. And then for the rotor RPM, I kept at a constant 900 RPM. This is in water, so to air it simulates around 10,000 rotor RPM, which is very common for most quadcopters. Over here on the right is the testing matrix with each of the test cases and the parameters that were varied. For each test case, the rotors were spun up for 1 minute. This is to allow them to reach steady state. Once the steady state was reached, data was recorded for 10 seconds, and then over that 10 seconds, the velocity was averaged, and that's what each one of these graphs represents for a specific test case of the average velocity. This is the dual rotor with the perpendicular configuration with the laser plane at the tip. For this specific laser plane position, we can see the high velocity of the blade, which is the kind of the red circle for each graph. You can see it kind of moves down as you increase the rotor angle and gets shifted further to the right as you increase the rotor angle. The next set I wanted to show is the dual rotor configuration in parallel to the crossflow with the laser plane position at the rotor hub. For these test cases, you can see the increased velocities for the inflow. You can also notice that there's a kind of a distinct dead region over each of the rotor hub, and this would be kind of an ideal, small ideal placement for sensors. The last one I wanted to show is the quad rotor and plus configuration with the laser plane positioned at the mid plane. This is the center of the quadcopter in between all of the rotors. And you can see there's a pretty steep increase in velocity, but you can also notice that there's a distinct kind of dead zone or dead region in the very center of the quadcopter, and this would be an ideal placement for sensors again. Then taking that velocity data, I plotted the vertical velocity profile for each of the test cases against the x distance moving down the test section, and then plotted it each test case for each of the laser planes, so you can see how the inflow velocities change as you move along the rotor system. For this one, this is the rotor in the dual rotor in the parallel configuration. The midplane and the hub had the two maximum velocities, with the hub having a distinct drop in velocity directly above the rotor hub, surrounded by kind of two maximum peaks of velocity. And then the midplane had a more single peak vertical velocity, as right at the center. Next is the vertical velocity profile for the dual rotor perpendicular configuration. For this one, the mid plane, which is the laser plane in between the two rotors, had the lowest velocity, which makes sense because it's in between the two rotor blades, except for the 15-degree test case where it almost matched the hub. Last is the vertical velocities profiles for the quad rotor tests. For this one, the mid plane, which is the plane in the center covering the leading and trailing rotor hubs, as well as the center of the quadcopter, had the maximum velocities. But for the first three cases, you notice there's this distinct dead region, which would be right in the center of the quad. And this dead region would make it ideal for sensor placement, as it's in the center of the quad system, and would make it easier for sensor mounting. In conclusion, the flow around multi-rotor should be considered for sensor placement. This research identified a small dead region above each rotor hub. This is a very small location that could be used for sensor placement. Research also identified a dead region in the center of the quad rotor system that's slightly larger. This region would be ideal for sensor placement, as it's in the center of the quad rotor system and would make it much easier for sensor mounting. For future work, we'd like to do more work with the ultrasonic ammonometers and quadcopters to test the effect on the actual sensor measurements. And we'd like to do more PIV testing in the X configuration as well as a single rotor configuration. Thank you very much.